Understanding radiator performance can be crucial to an automotive manufacturer. While a large radiator will sufficiently cool the engine, it can add unnecessary weight to the vehicle, impacting fuel efficiency. A smaller, lighter radiator can save weight, but might not have the heat extraction capacity needed to cool the engine to the proper temperature. So how does a manufacturer develop an ideal radiator? Automotive manufacturers and suppliers use CAE as part of their development process to simulate and validate the best radiator design for their specific application. Although CAE in general is much faster for evaluating a number of designs than trial and error with physical tests, the traditional radiator analysis process can take as long as 20 days or more from initial design through final system validation. This length of time spent for analysis is partially because radiator simulation is complex, involving coupling of fluid and thermal analyses. But the bulk of the time spent for radiator simulation is devoted to just building the analysis model. Engineers face three main challenges to building their radiator analysis models under traditional processes. The first challenge is working with the initial design data and developing the geometry that represents the air flowing around and through the radiator, known as the fluid domain. Typical CAE tools don't have the geometry capabilities necessary to do this step efficiently. Instead, engineers often use multiple tools to create the fluid domain, which can then lead to data transfer errors. Another challenge engineers have is with creating a mesh to represent the coolant tubes in the radiator. With typical CFD tools, analysts model the coolant tubes by manually building a hexahedral FE mesh for each tube. This process is extremely tedious and time-consuming since there can be as many as 50 tubes or more in a radiator. This method also creates a large number of elements, which leads to longer simulation times. The third challenge that engineers face happens when the design changes. When engineers need to simulate a design change or alternative idea, they must repeat all analysis modeling steps from scratch. Automotive manufacturers can increase their competitiveness by reducing process time and improving speed to market. NX CAE provides the means to reduce radiator analysis modeling time by as much as 90%. The following demonstration will show how NX's unique integrated environment allows engineers to speed radiator analysis modeling. With NX, engineers can easily create and edit analysis geometry, efficiently mesh the model, solve it, and review results in a fraction of the time it takes with other analysis tools. Creating the geometry that represents the air mass, particularly for the air in between the radiator fins, can be very difficult with standard CFD tools. However, NX includes powerful geometry editing capabilities not found in typical CAE tools that allow engineers to easily model the complete air domain within the radiator. Direct editing using synchronous technology lets CAE engineers edit complex geometry quickly and intuitively without the need to know the geometry feature history. As seen here, the engineer is able to quickly model the air volume in between two sets of radiator fins and then combine it with the rest of the air volume on either side of the radiator. The analyst can then quickly mesh the air that's flowing through the fins with a 3D swept mesh. Next, he meshes the rest of the air volume on either side of the radiator, including the air passing through the fan. Instead of manually creating a hex mesh for each coolant duct in the radiator, NX uses a unique method to model the coolant ducts using 1D elements. The 1D element mesh can be generated extremely quickly, as you see here in this example. This approach allows engineers using NX to shave hours off their coolant duct modeling process. With the mesh complete, the analyst applies boundary conditions to define convection between the radiator and air, coolant volume flow through the coolant ducts, the inlet and outlet temperatures of the radiator ducts, and definition of the airflow passing through the radiator and fan. Using NX, an engineer can build the entire radiator analysis model in less than half a day. Once the model is complete, the engineer solves the model using the integrated NX Flow and Thermal Solver. Building and solving the analysis model quickly means engineers have more time to evaluate results. To save engineers even more time, NX has the ability to create post-processing templates that will automate the generation of critical results views and reports. In this example, templates are available that allow the engineer to quickly see coolant duct temperatures, air temperature as it passes through the radiator, fluid velocity, and fluid streamlines through the radiator. After reviewing results, the engineer finds this radiator design is not extracting enough heat to meet requirements. To correct this issue, the team decides to add a second fan to the radiator system. With typical CFD tools, such a radical design change would surely require the engineer to create an entirely new analysis model from scratch, another multi-day process. But since this engineer is using NX, he can rapidly update the existing analysis model to account for the new design. The analysis model is associated to the base geometry, which means the analysis model will automatically update to the new two-fan design. This means the analyst can update the model, solve, and review analysis results for the new design in less than a day. As you just saw, NX CAE speeds the radiator simulation process by delivering comprehensive multi-CAD geometry editing capabilities, unique radiator meshing strategies using 1D elements for the coolant ducts, an analysis model to design associativity that allows for rapid design analysis iteration. More iterations and less time means you can deliver better products faster.